let me now try to answer the following question. How does biomass co-firing influences the energy efficiency of the plant? Because sometimes we ask ourselves this question, and let me try to answer this question in a more quantitative way. So how it really comes in numbers when we compare co-firing and combustion only coal, and also combustion only biomass. So let's try now to summarize a little what happens when biomass is added to the base fuel. So we have two groups of issues. First group is combustion related issues. I mean the situation which happens inside the boiler or local boiler. So we have the situation that the moisture content of the fuel blend changes. So the consequence is that the fuel blend calorific value also changes. And the consequence is again that the flue gas flow volume changes, as we have already told about that. And the combustion temperature changes because we have more water in the fuel. And so we have more moist fuel, and we have the higher flue gas flow and changed combustion temperature. And also, if the particles of biomass are larger than the particles of the coal, so they cannot be combusted in totally. So we have still unburned carbon content in the ash, in the fly ash. So the loss of ignition is higher comparing to the coal combustion. So the LOI may increase. And another group of things are the things related to the auxiliaries. So the extra elements which should be considered local plant, maybe not related to the boiler directly, to the combustion issues. So the biomass handling needs extra power because when we add the biomass handling systems, so we have to use extra electricity. So we have this extra consumption. Then we use extra force to mill the coal and biomass mixture. So again, we need the extra power. And as it already has been mentioned, the induced draft fan load and the electricity consumption to drive this fan changes. And the combustion air fan load and electricity consumption changes. So again, we have directly more consumption of electricity. So in my opinion, we should analyze both of these aspects, and I will try to do that separately. First, the change of the boiler energy efficiency, and then change the coefficient of auxiliary electricity consumption. And we can use two different coefficients to evaluate that. The first, we will try to assess the efficiency, the energy of efficiency of the boiler. So that's E letter stands for energy efficiency, and B is the boiler. And the reference case when we combust only coal, and the other case when we use the biomass. So COF means co-firing. So these two efficiencies will be used, and also here when we will consider the auxiliary consumption, we take this epsilon for electricity consumption coefficient in the reference case when we combust only coal, and in the second case when we add the biomass and we perform the biomass co-firing. So these two scenarios, first number one, another one number two, and these two scenarios should be applied for again two different situations. First situation is when we co-fire the biomass with the hard coal. This is the representation of the hard coal, and we co-fire with the lignite. Because in Poland and also in European plants, we can have two situations. As a base, the coal plants can use the hard coal or the steam coal, as it's sometimes used, this term, and also they can be fired with the lignite. So we expect that maybe there will be some differences in these two scenarios. and then we call it scenario A for the hard coal and scenario B for the lignite. And to answer these questions, what happens in these four different scenarios, so the combinations of four different variants, we used the input data which we gathered in our experience, in our industrial testings, when we used 12 different biomass sorts, the pellets, raw biomass, woody biomass, and the biomass as residues from the agriculture and also from the food processing industry. And we tested 6 different types of the boilers, the pulverized coal, and also different outputs of these boilers, smaller scale and the larger scale, and different configurations. And altogether, we performed a little around 120 single replant experiments. So we gathered quite a lot of different pilot scale testing data. And when we analyzed this data all together, we worked out the empirical correlations. And let me share the conclusions. So first, when we take the scenario 1A, so we combust the biomass with the hard coal, and scenario 1B, when we combust the biomass with the lignite, and we take a deep look into the efficiency of the boiler. So the situation is, I would say, opposite in these two cases. And in the horizontal lines, you can see the biomass share, but this time it's not the mass share, it's the energy share. I will later on show how to recalculate the energy share into mass share, or the other way around. So we have biomass share in the fuel blend, and here these are this is the efficiency of the energy efficiency of the boiler while co-firing, divided by the efficiency of the boiler when combusting only coal. So these coefficients are divided one by one in these two graphs. On the vertical line, we have the same configurations. And look what's going on here when we take the hard coal.
Let me ask you for something. So it means that, for example, for burning coal, when we have 15% of share of the biomass, we can expect that the efficiency of the boiler will rise by 80%.
That's the efficiency of the co-firing, and that's the efficiency of the when we combust only
Yes.
coal. So when we are here, nothing changes. Yes. And when we go up there, we observe that there is a
Yes.
change, and there is a change in the and there is a change with the efficiency.
So it's actually increasing dramatically.
But I would say more interesting is that yes, but more interesting is why it goes like this. So why it goes like the parabol. I would say it's we found the following explanation here. When you are adding the biomass up to 15% on the energy share, then your efficiency goes down. Your efficiency goes down. But when you reach let's say the critical point here, and the efficiency starts to behave in the other way. Why it's like that? It's because your installations here are not able to co-fire more and more biomass. So the system responses in the lower efficiency. The lower efficiency here and means that there is more and more biomass, that gives you the effect that your boiler is not it's not operating well. So the energy input in the boiler is changing. So that's why when you take this actually two percentages and 2% here, it behaves like this. So the crucial is, let's say, this 15% on the energy share. I would say there's it can be said that it's a strange, but that's what we have found. And the comparison with the lignite is different. So it's like you can easily imagine why it's different here, because in this situation, when you add to the coal, when you add the biomass, you add the worse fuel to the better fuel. The coal is better fuel. The hard coal or the steam coal is a better fuel than the biomass. And here, when you have the lignite, in most of the cases, the Polish lignites have the lower heating value than the biomass which is added. So in this case, the biomass is the better fuel in terms of LHAV than the coal. So the situation is the opposite. And let's if you want to dig more in these issues, there's a book which gives more information on that. You can dig in more details. Let's now have a look in the same situations, in the same scenarios. So again, we have the hard coal A and we have the lignite and the B, and the situation is similar, but this time we observe not the efficiency, not the energy efficiency, but we observe the coefficients of electricity consumption by the auxiliaries. And again, the symbols are the same. Reference, the co-firing case and the reference case. The co-firing case and the reference case. And when you again add the biomass to the co-firing, then your efficiency goes down, your consumption goes down, and when you go up, it's the opposite. It's the opposite way. So that maybe the one thing which should be remembered is that we have two opposite let's say behaviors of biomass and added to the lignite or added to the hard coal. Yes, and this is just a table to recalculate the energy share to the mass share. And when you this is actually depending on the LHV of the base fuel divided to the LHV for the biomass. And here you have the energy share, and here you have the mass share. So if you want to recalculate from the energy share of the given value for such coefficient of this coal LHAV to the biomass LHAV, you can find the number here. Of course, it depends how much your coal is better than the biomass in terms of LHV. Here you have the 10% more, the coal to biomass. Here you have the 20, and the responding values are presented here. Okay, so it is just for the help to show the or to recalculate the energy shares. Yeah, this is just the explanation. If the LHAV of the base fuel is the 20% more, the energy share is 15, and the mass share is a little more than 21%. It's just when you want to recalculate, the simple calculator. Yeah, that's this number. Let me then draw some conclusions. So when we have the biomass addition, we influence the co-firing boiler energy efficiency and its electric auxiliary needs. And the effects are opposite when we are co-firing the biomass with the hard coal and lignite, which is the low-rank coal. It can be performed not only with the steam coal, the hard coal, but also with the lignite, due to generally worse in case of coal and better in terms of lignite, the parameters of biomass comparing to these base fuels. Also, these effects are not only depending on what kind of fuel you use as a base fuel, you are the coal or the lignite, but these effects also are influenced the properties of the biomass in terms of if it's a raw or it has been pelletized or maybe it has been dried. What we have found looking at the biomass combustion fluidized boilers, that generally the fluidized boilers are more convenient, let's say it in this words, for the higher share of biomass. They are less sensitive, although they require more sophisticated boiler and fuel handling control systems comparing to the pulverized coal. This is what we have observed. And also improving the properties of biomass in terms of the grindability, as Janusz Lasek has already said, when we apply the torrefaction, then the biomass parameters can be improved in terms of the grinding. We use the electric grinding, or at the same time where we implement some dedicated biomass routes. So instead of the ball mills, which are normally used for the coal milling in coal-only plants, we apply hammer mills. We have some biomass combustion plants in Poland when we apply hammer mills, and that's the way to minimize the boiler energy efficiency losses. And you can say that generally co-firing the biomass with the coal may record in no loss of boiler efficiency when we adjust the combustion output for the new fuel mixture, especially for the shares which don't exceed 10% mass. Of course, the situation is different when you do the trial testing. So you just add the biomass to the coal and then you combust it. So you have not prepared installations. Your mills behave in the same way as they behaved when the coal milling. Your transportation systems behave at the same way. Your boiler responses at the same way. So it can behave very strangely and the efficiency may go down very strongly. But when you optimize it, when you adjust your combustion, when you adjust the injection of the water to the steam, when you optimize the boiler, then it's even possible for the boiler to combust 10% mass of the biomass and no efficiency could be observed. So there is really a big change when you do the trial testing, and then after some optimization, when you combust the same share. So you can really optimize it in a very dramatic, let's say, way, and combust the biomass with the 10% of the mass, and no efficiency loss can be observed. But you have to work out quite a lot on your boiler behavior, on your milling, to implement new procedures in the mills, in the boilers, especially in the side of the steam. Yes, and also when you compare the biomass combustion to power plants, which are burning 100% of the biomass, sometimes you can ask the question, is it better to co-fire the biomass, or maybe is it better to combust only biomass? Is where the total energy conversion efficiency is higher, where it's more effective in terms of electricity generation, for co-firing or for 100% combustion? With what route is better, which gives the better efficiency?